Hello, geometry students. Mr. Zacek back and better than ever. And we are in lesson 4 of unit 7. We're talking about similarity and right triangles. And we're looking at kind of a specific application of this idea of similarity that's going to give us an opportunity to explore the relationships that exist in this setup. Okay, so here's the theorem. The altitude, remember an altitude is always drawn from a vertex perpendicular to the opposite side. So in this picture, CD is the altitude. The altitude from the right angle to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. Okay, so what you see here in this diagram is we've got triangle ADC, we've got triangle CDB, and we've got this big triangle ACB. And basically what we're saying here is, here's the setup, okay? The setup is, number one, we have a right triangle. Number two, we have the altitude drawn from the right angle to the hypotenuse. And you want to remember in a right triangle, the hypotenuse is always the longest side. Okay, so when that happens, all of those triangles are similar. So all three of these triangles are similar to each other. And you can see that there in the similarity statements. Okay, now this is a proof of that, what we've just said, and I'm not going to go through it, but you can read through it on your own here. All this proof is doing is it's just establishing, we're proving the triangles are similar using angle, and showing you that all three of those triangles are similar. Okay, so now when we're solving these things, what we're going to realize here in this relationship, this is where the term geometric mean comes in. So proportions in which the means are equal occur frequently in geometry. For any two positive numbers a and b, the geometric mean of a and b is the positive number x, such that a over x equals x over b. This is where we get from the cross product property, the product of the means equals the product of the extremes. So as an example that we might look at is, let's say A is 4 and B is 9, and we're trying to find the geometric mean. So, well, that's 4 over x equals x over 9. So we do our cross product property. It's the product of the means equals the product of the extremes. It's the cross product property. And when we take the square root of this, we get x equals positive and negative 6. Well, geometric mean is the positive number, so it just be x equals 6 is the geometric mean of 4 and 9. So normally, before this point in our math language, if we use the word mean, we were referring to the arithmetic mean, which is average. So when we've said the word find the mean, we mean find the average. So now we're using a more specific term called the geometric mean, and this is how we would go about finding it, okay? So in our in that, then we have some relationships that exist in these things. So the first one, corollary here, is what we call SAS, and it's the length of an altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. So as you look at this diagram, you see that AD is the extreme, DB is the extreme, and CD is the mean. Okay, so it's the product of the mean. So CD is the geometric mean of those two lengths. So we use this phrase called Hills and Sass to remember it. And so in the big triangle, L1 is a leg of the big triangle. L2 is the other leg. The A stands for the altitude. And S1 is this part of the hypotenuse. S2 is the other part of the hypotenuse, and H is the whole thing. So when we have the altitude is the geometric mean of S1 and S2. Okay, so this is a phrase that you can use, SAS. Okay, the A goes in there twice for it. The other relationship that we have is what we call hills. And so in this case, the altitude to the hypotenuse separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to that leg. Okay, so let's look here at our diagram. Now here's what I want you to see in this one here. The leg that we either know or are looking for, and notice this, S1, it's the adjacent length down here. Okay, so if I was going to use a highlighter, I would say, okay, L1, that's this and this, is the geometric mean of S1, the adjacent length, and the whole hypotenuse, which is our H. So then when we come over to the other side of this, we see leg 2 is the geometric mean, but this time it uses the other adjacent side, which is side 2 down here. So that's the difference between these two formulas. The yellow one, L1, is connected to side 1, which is the adjacent, and the L2 is connected to side 2, which is the adjacent. And then H represents the entire length of the hypotenuse. Okay, so the way that we kind of remember this is we say hills and sass. Hills and sass. So you want to be able to draw this diagram when you're taking a quiz or you're working on your homework. You want to be able to draw this diagram and remember hills and sass as a way for you to set up the right proportion to be able to solve this question. Okay, so let's do some example work here and kind of put this thing into action. All right, so write a similarity statement. What similarity statement can you write relating the three triangles in the diagram? So again, sometimes it's helpful to draw these triangles separately. So here we've got W, Z, Y, and notice that angle Z would be congruent to there. And then over here we've got kind of X, W, Y. So let's put this as a 2 marker and a 2 marker. And we know that they're all going to be similar to each other. So that means that Y has to have 2 marks. And that means that this Y over here and this one has to have 1 mark. Okay, so we could say triangle. Let's start with our large triangle. X, Y, Z is similar to triangle. If I started with X, I'm going to come down here and I'm going to say Y, W, Z. Okay. And then triangle XYZ, again, that's the big triangle, is similar to X is the 2 markings to the right angle. So XW, XWY. And then those 2 triangles that I drew separately are also similar to each other. So if I did ZYW as an example, it would be similar to triangle. So if I started with Z, I need to start with Y, and this one, YXW. Okay, So we've got a bunch of things that we can recognize. And if they're similar, they're proportional. Now, when we get into this one here, now we're looking at our hills and SAS thing. So let's see if we can draw that. You might need to kind of flip back, but basically here's our setup, okay? And we're going to call this L1, L2, S1, S2, altitude, and then the whole thing is going to be the hypotenuse, all right? And so our things are hills, so if it was leg 1, it would be side 1, and SAS, side 1, altitude, altitude, side 2, okay? And for the hills, if it was leg 2, it would be side 2. So now, when I'm doing this question, sometimes I can't do this with a board, but what you might want to do is just pick up your sheet of paper and turn this over, and you realize that y is the altitude. So that's our SAS. So the way we were to write that, so this is really like side 1, side 2. So the SAS would be 12 over y equals y over 4. So we cross multiply, we get y squared equals 48. And we take the square root of that. And in this case, I'm not worried about the negative square root. I'm going to simplify this. That's 16 and 3. So y would be 4 times the square root of 3. All right, x is leg 2. So that's going to be our hill. Now, in order to do the hill, I need the whole hypotenuse, which is going to equal 16. So again, hills, it's hypotenuse over leg 2, side 2. So it would be 16 over x equals x over 4. So we do the cross product property, x squared equals 64, take the square root, and again, we're only taking the positive square root because we have a distance, and so x is 8. All right, so number 3, same kind of thing, so I'm going to go ahead here, I'll just use a different color. I want to think about, okay, this is going to be my side 1. If that's side 1, we'll call that leg 1. Side 2, get the whole hypotenuse, which is 9, and a, there's our altitude. So I'm going to do my SAS first, which would be 4 over y equals y over 5. So y squared equals 20. So the square root of 20. Let's simplify that down. It's going to be the square root of 4 times the square root of 5, which would be 2 times the square root of 5. And then for x, that's a leg, so that's a hills. Hypotenuse over leg 1 equals leg 1 over side 1. X squared equals 36. Square root of 36 is 6. Again, only taking the positive root because we're dealing with a distance. All right. So now we get into an application question. Love this. This one's shown up on the Regents exam a bunch of times, this type of question. Whoops. And it's our final one for this lesson here. So in the diagram below, the line of sight from the park ranger station P to the lifeguard chair L on the beach of lake is perpendicular to the path joining the campground C. So basically what they're saying in this is, let's recognize that this is an altitude. And the first aid station F, the campground is 0.25 miles from the lifeguard chair. The straight path from both the campground and the first aid station, the park and ranger station, are perpendicular. So what we want to do, again, this is on your final exam or your unit test, is we want to recognize, number 1, we have a right triangle. Number 2, we have the altitude to the hypotenuse of that right triangle. Okay, so we want to be thinking hills and SAS. Okay, we want to be thinking those things in this question. All right, so if the path from the park ranger station to the campground is 0.55 miles, determine and state to the nearest hundredth of a mile the distance between the park ranger station and the lifeguard chair. Okay, so we are trying to find the park ranger station, which is P, to the lifeguard chair, to the nearest hundredth. Okay. Well, in this scenario, the altitude here of this question now, this is actually just simply a right triangle question. So this isn't a Hills or SAS so much as this is A, B, and C. We want to be thinking Pythagorean theorem. Okay, A squared plus B squared equals C squared. So A squared plus 0.25 squared equals 0.55 squared. All right, so we've got that. So let's go ahead and just kind of solve this question here. So I'm going to do 0.25 squared is 0.0625, and 0.55 squared is 0.3025. So I'm going to subtract 0.0625 from that, and A squared equals 0.24. And then I'm going to take the square root of that number, and A is going to be 0.4898. And what did it say? To the nearest hundredth of a mile. So we're going to round up this to a 9. So it's going to be 0.49 miles would be the distance. Okay, so equals 0.49. Now, Gerald believes the distance from the first aid station to the campground is at least 1.5 miles. Is Jared correct? So the campground is which number? C. So really here's where we're trying to figure out what is the distance of the whole hypotenuse. Well, that's our hills. So this is H, okay? And let's call this leg 1, side 1. So H over 0.55 equals 0.55 over 0.25. And so let's go ahead and just, cross multiply and cross product property and see what we get. So 0.25H equals 0.55 squared, or 0.3025. So we divide that by 0.25. And we get 1.21 for the length. So Gerald believes the distance. Is Gerald correct? Okay, Gerald is not correct because the distance is 1.21 miles. Alrighty, so listen, this is a popular one. This is one you're going to see a lot on problem sets, this Hills and SAS things. It's a little bit tricky, so you really got to study to get that diagram down and remember how we set these different relationships up. All right, good luck. Let's ask and keep on asking, and I'll see you soon.